the graph engine is a different kind of storage engine for MySQL, which is more, as the term that Aaron and myself have agreed on, it's more of a computational engine rather than a storage engine as such. Insofar that you're interested in querying new generated data out of it rather than just getting out what you put in. Of course, there's a lot of applications for this with data which requires processing properly, statistical analysis of a large statistical analysis you want to go through, do such things. But for now, we've just got the graph traversal, which is an interesting problem in itself. Next slide. Yeah. Okay. What do we mean by a graph? Typically, we mean something which is in some kind of hierarchy, not necessarily a tree, but basically where you have nodes and edges, edges linking them.
So graph in this sense does not mean drawing or chart?
No, it means linking nodes and edges.
Okay.
This could be like categorizing. In this case, it shows that you have a super category of food, of which you have fruit and vegetables derived from that, and then into types. Or you could even have, say, types of books. You have reference books, and then what kind of reference books? Oh, these are teaching textbooks. Those there are data sheets or product specifications. You can drill down on things, for example.
Okay.
So there's a clear hierarchy of some form.
So what about when the hierarchy is more messy?
Well, again, because the graph engine is more generic, it's basically, in any case where you have nodes with lines linking them, the graph engine will represent it.
Okay.
In practice, even though it doesn't show it here, how the graph engine is implemented is that you would need two edges to denote a bidirectional link, because all edges in the graph engine are unidirectional.
Okay, so does vegetables have two edges there?
Well, this is just an example of what kind of thing.
Okay. Maybe I should let you go on.
Yeah. Next one. What we're talking about is, in a sense, like saying we have a network where you have a free-form structure of nodes which are linked by some way by edges. You can then, what you want to be able to do is find the...
one question about the graphs. Do we have a good documentation of the graph engine? Because if we add it to the MariaDB, we need to point and copy the information or point documentation
if you
somewhere.
look on if you look on our query on the our query website, the OQ graph, there's openquery.com.
There
is some, yes.
Yeah. So, and it's good enough.
It's good enough that you started. It shows you every single use case at the moment.
Okay, thank you. We'll see you in a short while.
Yeah. In this case, there's in a network diagram like this, there's no clear hierarchy as such. It's all that appears and how they're connected. But you want to be able to find the route from the shortest path from one node to another. And this is what this is the kind of problem the graph engine can solve. And the example at the bottom, Fender of Fen networks where you have people who know each other.
Or like, what is that, LinkedIn, where it shows you how many...
Yes, but this is actually a little bit more sophisticated than that, because you can actually put weightings between the edges.
Oh, this is like the old UUCP routing where the nodes would have like a cost.
Yes, you can put a cost on each edge.
Okay.
Okay, so it's a little bit more sophisticated than...
Oh, it sounds very sophisticated.
So next slide. The other thing is using the graph engine to resolve hierarchical graphs, basically where you have a directed graph. Rather than having omnidirectional, bidirectional edges, you have a directed edge, and so you can then traverse up and down the graph. It's basically like a tree. And of course the classic case of how many points for the Kevin Bacon test can be done on such a thing. This is a very common computer science problem to show that there is computational complexity in these things. Next slide. Okay, traditionally there have been various ways proposed to solve hierarchical graphs in different SQL or database environments. There are actually a couple of dedicated graph databases available, but they require quite a complex learning curve because they are their own thing altogether. For example, there is one which is available in the Java language, but again, you have to link to it. You have to.
Damn it! You were going to use this room, but you're here.
Oh, well,
You could just change your talk to this one.
anyways, but those require you to write your problem in Java and write it against these libraries in Java, and that can be a quite steep learning curve in itself. And the most popular one available is written in a very unfriendly license, which will require you to pay licensing fees if you use it in any commercial setting. It's written using the AGPL, which is not very user friendly, should we say? Of course, Oracle has their connect by prior to trying to denote how to traverse the graph, and then there's the recursive syntax in the SQL standard. But both of those have fought with their own problems. That the biggest complaint is that they're sometimes overtly complicated to use, and the performance is not much better than actually doing the brute force selects itself and writing a stored procedure. So what we want to do is have something which is a bit better than that. Yes. Okay. That's a picture of myself and Arian. Arian came up with the concept actually for the graph engine about 3-4 years ago, but I was busy doing other things and I didn't step up to write it. But this most recent version, which we're calling version 2 of the graph engine, is a complete rewrite which I did myself last month. It's a nice friendly GPL2 license, so people can pick up and use it however they like. And doing the selling point for Arian, OpenQuery is hoping to sell support and engineering enhancement services for it. But otherwise, the goal is to provide improvements to the open source community with GPL2. So, like I say, it's a computation engine. The idea is not about persistence of the data, although we're thinking about how to make a persistent graph engine. Basically, the data is stored in RAM, a bit like the memory heap or heap table store. But what we want is something which is fast and reasonably memory efficient, so you can put reasonably complex graphs in the computer's memory. And as a result, the number of the data you get out of it is basically computed based upon the data you initially inserted into it. So, as Owen said, it could be considered as the magic view of some computational intelligence behind it. How the code is currently written is that it's available for as a drop-in for MySQL 5.0, so it's actually including the sale binaries for our Delta sale binaries, which are going to be used by OpenQuery and multi-program as a Maria binary distribution. So if you are using the Maria binary distributions, if you get the sale version, the sale one has bleeding edge code, and the graph engine will be included in those. For 5.1, it is hopefully going to be available as in the binary package for MariaDB, and also you can build it yourself from the source code. And all the source code is available on Launchpad. Just do a search for OQGraph. Basically, the way how MySQL communicates to the graph engine is by having this table structure here. As you see, it's a very simple table structure. Basically, you have to fit your data to both conform to this way. In essence, there's only really 3 pieces of data you put into the graph. So basically, this column, and this column here. The other columns are actually computed columns or parameters to drive the graph engine. So when you're inserting your data into it, you specify the start of the edge and the end of the edge and the weight. If you don't specify the weight, the weight of 1 is assumed. And so this presents a really nice, simple view for querying data, and then you can join on it, as we will see later. Slide.
How long does it last, that table you just created?
If you do create temporary table, it will last as long as your session. If you create table, it will last as long as the server's up, or the data will. The table will exist again when the server is restarted, but all the data is lost, like if you have a memory table.
Okay.
The table is not transactional. It's just like memory table. It's non-transactional. But writes are considered atomic. So when you do a write, it will get the whole table lock, just like memory table does. For best performance, it is recommended if you can, if you create it as a temporary table, so that you don't have multiple users contending on the same table. But if your data is pretty much static, then you can have a shared table because multiple readers can read from the same table at the same time. So the same limitations as what you have with memory tables on their use. And as a simple example, inserting edges with weight 1 is just a case of inserting node IDs into the table. It's not very imaginative, it's just pretty straightforward.
So, right, so the last point on the first bullet, so 1 to 2 is the same thing as 2 to 1.
No, these are, when you insert them like this,
yeah.
it is only inserting a single unidirectional edge.
Oh.
So if you want to link it both ways, you have to have a 1, 2 and then a 2, 1 as well.
So for right now, that'd be at the application level, you just make sure that you insert.
If you want to have a bidirectional link, you have to insert 2 edges.
Okay, cool.
That way we kept the design simple.
Right.
Okay, next one. If you want to query what edges you have in the table, just by doing a simple select, you will get out your data you put in, except you see the weight column will be set as 1 if you didn't set the weight. And the other computer columns like sequence, link ID, and latch are just, well, those two are null, and the sequence will be just an increasing number. It's just to keep reference on how things. But because of the way how the store is, you can't guarantee the order that the data comes out. It could be any order. It's just that all the edges are there. It's just splat, here's the data. So that is, you can use that as a way of storing your edges so that you can restore it later. So that is supported. Next slide. Querying a simple path, and this is using a short. Well, they actually provide 2 different algorithms for shortest path computation. There's the Dijkstra's shortest path, which takes into account weight, and then there's simple breadth first search, which assumes a weight of 1. For when you do have all the weights of 1, the breadth first does work out faster. But if you do have varying weights, then you of course use the Dijkstra's. In many cases, you sometimes want to use both, because sometimes you want to know the least cost path, but then you want to also know how many hops it is to do it.
Right.
So you can use a combination of both. When you're selecting it, you basically select from the table, you select what algorithm you want, and 1 is actually the Dijkstra's shortest path algorithm. You set where you want to start from and where you want to finish up. And then it will just return as many rows as well, the first row would be the starting node, and it will return as many other rows for each edge it has to traverse.
Gotcha. With
the link ID being what node is it currently standing on. So here the sequence number is just an increasing number. So 0, 1, 2, 3, that is basically an increasing number of how many of the row count, which is the data is being output. And the link ID, you can imagine it like the origin ID is 1, this ID is 6. Right now it's standing on node 1. And then it traverses onto node 2, then 3, and it goes to 6. And that's the path it has chosen. Now, this here is just a little bit of prettiness. You can use group concat in order to just give you a nice single value result of the path that is done. Okay.
The format for original ID and destination ID, that is a big int?
Yes.
Okay.
So you can have any 64-bit value there.
Okay.
And of course the link ID is the same type.
Okay. So you said 64-bit?
Yeah.
So we could use MD5 sums of, or what is
It just has to be unique.
Okay, gotcha. Cool.
Other things as well available is it lists all the nodes which you can, using the web algorithm you've chosen, to end up where you can finish at node 4. So this is all the nodes you can start from which will reach that node.
Mm-hmm.
And conversely, all the nodes which, if you're standing on node 4, where can you reach?
Oh.
This is especially important if you don't have if all your edges aren't bidirectional.
Mm-hmm.
This is how you want to do if you have a hierarchical tree. Okay, so those are provided for convenience. Next page. Okay, we do have documents for explaining what different latch values are. As I explained earlier, latch 1 is Dijkstra's shortest path, which is denoted by this function here as to how fast it is. It is recommended to only use Dijkstra's when you've got weights which are not all 1. If you have all your weights at 1, the breadth first search function is recommended as more times memory efficient. You can also available is the ability to update and delete edges. So not only can you insert your edges, you can update and delete them. Although, because of the way how the cursors are implemented, it is recommended that when you do update and delete, you either change a single edge, or you make sure you're not updating the starting or ending edge nodes of an edge. Otherwise, you'd find that you can do some pretty odd things to your data because it gets lost when it traverses the graph as it tries to update the data. Yeah. If it doesn't crash, it just doesn't update the data how you expect. So if you're only updating, say, if you set all the weights to 1, that is safe. You can do that because you're not updating the starting and ending points of any edges. Okay. Next.
Is that it?
Is that the last one? Okay.
Oh wait, no.
Okay.
There we go.
Yes. Okay, common use for it, rather than just acting just a number, you'd obviously want to make it nice and pretty by using a join. So you have a name, associate some data with each of the node IDs, and then you can join them so that you can now traverse it and get nicer data out of it rather than just the node IDs. And that's just pretty much the standard join. Next slide. A good example available in the source repository, although I'm going to fix up in the docs because the docs are a bit out of sync at the moment. I'll push those. Give me 15 minutes or after this and I'll push the changes to that. But anyways, there's a Tree of Life, which is basically the data from the Tree of Life website, which has some 90-odd thousand species listed in there and how they are related. And then you can then traverse that graph. The current documentation is a bit inaccurate in that it says it can take several minutes to do this, insert the data into the graph, but some performance improvements have been done. It now takes seconds rather than several minutes. In total, after you work, there's 178,000 edges.
Wow.
And traversing the graph is actually quite quick. There's an example, should be an example. Next. Okay, this shows an example of execution of basically taking two different node IDs and the result. And it doesn't show it there what the execution time is, but I can actually show it on this machine here. You're looking at, to do this query here, and remember you've got a graph of 170,000 edges. To do that traversal, to find from one point to another like that, would take it on the order of, you can do probably about 100,000 of these traversals a second on a graph of that size. So it's not too slow.
No.
The slowest part is actually the round trip time of the MySQL protocol.
Oh wow.
For a graph of that size, it starts to get a little bit more hairy when you have millions of edges.
What's the limit you guys have pushed it to?
Iron has managed to load a graph of 11 million edges.
Wow.
Then he runs out of memory. No, we have plans in the future of having a version which is not so constrained by actual RAM and actually persist the data on disk. And we are hoping to be able to have a design which will be limited to around 2 billion edges, and that would be a data store size of around, I think we're talking about 48 gigabytes for 2 billion edges. But that is not yet done. It's just a common plan.
Okay.
Okay. Slide. Oh, this is traversing two unrelated species. So this is a much harder job. Unfortunately, I think the original slide actually did show the time that the execution would take, but I think the font size took taken off.
Kind of falling off the bottom.
Yeah. No, I forgot to put it. Anyways, no, even that traversal there, going all the way up the tree and down the other side, is pretty quick. So, again, generally we found generally on traversing a graph of that size, like I said, about 100,000 queries of that type per second can be done, and that data is not cached.
Okay.
So it is performing that traversal. Next one. Here's just another example of its use again.
Cool. Can you have multiple like networks? So if you have,
if the networks aren't connected,
yeah,
yes.
and it's not going to cause any problems like that.
No.
Okay. Cool.
It just means that you have a single table with a lot more data in it, and it's just you have islands of nodes,
Right.
which there's no way to traverse from one island to another.
Okay.
When you specify a query of which there's no way to traverse from one island to another, you end up with a null result set. No values are returned.
Okay. So if you wrap, basically, if you're saying are we, you would wrap this whole thing in a count.
Yeah.
And if it's greater than 0, it's true.
Well, yes, there is a root.
Okay.
Of course, there's actually slightly more efficient ways of doing that, but yes, in essence, that is what you can do.
Okay.
Another example I included is a generic maze building test, which he builds a maze of which he then tries to traverse from one side of the maze to another. In the largest maze he has tried to date, we're talking 1 million rooms in the maze. To traverse the maze had 170,000 hops, and that took about a second to execute to find find the root of which traversed 170,000 edges. So that gives the idea of its performance. There is some performance. The point that you're talking about whole seconds to traverse a complex graph like that, but again, 170,000 edges to traverse to get from one end to the other. That is pretty decent, I think.
So it would give you a traversal path. You could just say, here's the
Here's
entry
where I'll
node and the
start.
exit node,
Yeah, and it'll find the route to get from one to the other.
or routes if there's more than one.
Well, actually, it only finds the shortest route this time.
Aha.
And there's two algorithms for shortest route. There is the Dijkstra's, which is takes into account the weight, and then there's the breadth first, which just assumes the weight is 1. So they're the two algorithms currently provided.
Do you have plans to do all unique routes from one node to another?
That has a information blowout, which can be huge.
Right.
And it's not really that practical.
Yeah, I don't know what you'd use it for other than knowing.
Yeah. If someone can find a use case for it, then we can probably do it. But at this time, I can't think of a reasonable use case for that because of how quickly the information will blow out. You end up having n to the power n rows being returned.
Yeah.
So it's it's just the next page. Okay, so this is where he has an example of his mouse walking through the maze and the result of it.
I like just the pun of having concat with the mouse.
Now, the current implementation uses about 60 bytes per edge, and that's a rough estimate based upon looking at the memory consumption of the MySQL servers. In the future, we have plans of creating one which only uses 24. The disk persistent version, we're looking to have only 24 bytes per edge. So that's why we're looking at about 48 gigabytes for 2 billion edges. That's where that comes out. Again, like I said earlier, it behaves like the memory engine, and that it is table level locking, but shared read. There's no locking for temporary tables, there's no persistent at and there's no support for transactions. But for most people, that is perfectly fine. Insert performance is actually, this is a bit out of date. The insert performance has been improved. It now is a lot better than that, which is why inserting the tree of life now takes about a second rather than the several minutes it was before. So that has to be updated. So yeah, as an example, so you can show use init file to start up. You can do what you like. I think that's the last slide. Is there another one? Oh, persistence. Yes, I explained how I was thinking about going back to persistence. 16 bytes per edge was a little bit optimistic because that was only bi-directional edges. For directed graphs, actually we're looking at 24 bytes per edge. And we want to try to make it remain fast, or at least as fast as current implementation. And REM wants to try to see if you can get people to pay for this as well as the persistent one.
Yeah.
That is probably the last one. Is there another one? I don't think so.
Well.
Oh, this is, okay. The Launchpad site, we can grab the current source code. Binaries and packages are available now, Delta. So hopefully that is of use to people. And if you want to see it running, I could briefly demo it on my machine here.
The binaries are MySQL and MariaDB bundled with.
They are basically the MariaDB distribution. Monty is enlisting Aaron's help in putting together binary packages for MariaDB.
Okay.
But if you want the MariaDB packages which have the graph engine in it, you need to have what are called the SAIL binaries. These are the binaries which include experimental features.
Okay. They're called SAIL?
Yeah, the ALDelta SAIL binaries.
Okay.
As in the sail of a ship.
Oh.
SAIL.
Okay.
Okay. So the standard binaries are the standard MariaDB binaries do not include this because Monty wouldn't have it in it yet.
Okay.
But as soon as if Monty is happy with it, then it may go into the standard binaries. We'll see.
Cool.
But basically, the standard binaries from ALDelta are the binaries as Monty wants them, and the SAIL binaries are everything else we managed to throw in. Okay.
Have you guys done anything like implementing graphics generation out of the islands that come? Because I'm thinking like you have a social networking site as like a use case, and there are clusters of people that are like islands.
Yeah.
And running this into graphics to generate a visual map of where those people
There's
are.
no reason why you can't do that, although representing the weight may be a bit more complicated. But there's no reason why you can't take the output of this and feed it straight into GraphViz.
Okay, cool.
Or at least I can't think of any reasonable reason.
Yeah, no, seems like...
GraphViz is very simple. You can, in the simplest case, it is actually possible to generate a single select statement which will output a string which GraphViz can pass. If you use the group contract, for example.
Right, okay.
It should be possible.
Okay. I'll play with it, and if I come with anything, I'll let you guys know.
Yeah. Already Arian has been in contact with some person who's trying out its use, and they have an Oracle database which has a hierarchical graph represented in it. And currently, traversal in the Oracle database takes a minute, but the same graph in the this graph engine takes seconds.
Wow.
So it is a order of magnitude improvement in performance. And that is with experienced Oracle programmers who are unfamiliar with MySQL but decided to give this a try.
Yeah.
Cool.
Yeah.
Very cool.
So I came in a little bit late, but when we're looking at graph engines and Neo4j, we looked at, and there are a lot of appealing things about it other than the license, which is why we stopped looking at it. But then one of the things that we really need is to be able to associate attributes with the edges and somewhat arbitrary attributes with
Well, for this, that we recommend each edge, or each node is represented by a each node is represented by a big int, a 64-bit value, and each edge is represented by basically two 64-bit values, and that is what the key for the edge is basically the origin node ID and the destination node ID. So the recommended way to keep the code simple is if you want to associate specific data with edges, you need to create a table which sits alongside of it, which has the correct primary key to associate with.
Yeah, so what we're trying to accomplish, I mean, it is quite straightforward with the Neo4j API is we want to, it's what we do. So we do host and speech recognition applications, and so we're handling all these phone calls that we automate, and so events happen throughout the call flow, and you get like matches and no matches on grammars, and you have confidence levels for those, and we want to kind of look across a call flow, like across millions of calls, looking across all these call flows. There's some predicate, and for how many of these is it true? You know, where how many are there where people no match multiple times in multiple nodes, and their kind of success rate in getting through a particular call flow. And we're trying to kind of tune our applications.
At the moment, we only provide two graph traversal algorithms, although we are currently trying to design a nice API so you can plug in your own graph traversal algorithm. That is not yet done. I presume that's what you want, a graph traversal, a custom graph traversal algorithm.
Maybe. I mean, what we were looking at would look straightforward with the Neo4j APIs. You can basically say, establish a condition and basically find out how many of these. Oh, yeah, it's a little bit different scenario of like we've got all these call flows that are essentially graphs.
Yeah.
Each one independently is a graph. So like it's a graph of colors path through the application essentially. And we want to compare across a large number of these graphs how many of them have particular characteristics in common.
Oh, so you're looking at, no, this currently doesn't do that. This is at the moment as it's currently is basically for graph traversal. For basically comparing paths, what you may be able to do is to combine this with the the spatial stuff.
Vodka.
And I even took a little bit of good risk to bribe this guy regarding parser. So he can see the true light and the true future of databases and parsers.
So what kind of vodka is it?
Sorry?
What kind of vodka?
Finlandia and Stolichnaya.
Really? Finlandia is from that country.
It's that's all I heard about it. It's all
yeah. Go to Sweden and turn right.
So what you may be able to do, if you look at the spatial stuff, which is in MySQL, there is a way of describing a path, and I'm not sure if there's any path comparison stuff done
You could
yet.
parse the stuff coming out of the path, maybe.
Yeah. So what you'd be looking at is storing. You have a graph, and then you're storing in a separate table the different users' paths through the graph. I have to look into it because I'm not sure how complete the spatial stuff is in MySQL, because it was done up to a certain point and then development kind of stopped.
Okay.
It's as far as I know, it's not even compiled in by default because of its current state. But it could be worth looking at.
But the unidirectional links that you put in, what happens if you have like a circle and then you say, show me the shortest path from...
It will find the shortest path going around using any legal path it can to get to from the source to the destination.
So it won't get stuck in a loop and just keep spinning around. Okay, cool.
Well, that's the shortest path, not the longest path.
Right, right.
It will find the shortest legal path.
Okay.
Okay.
Do you use Delaney numbers in it?
Hmm?
Delaney numbers? They're part of finding the shortest path.
No, what it uses is in the breadth first. It basically keeps a log of what nodes it has seen already, so it won't traverse further from the node it's already gone through. And in the Dijkstra's algorithm, it is basically a graph coloring algorithm. And so it colors the graph in order to make sure it doesn't get stuck in any local minimas.
I know the math end better than the programming end.
Ah, okay. Well, the Dijkstra's is pretty well established as a good algorithm. It's not the best, but it is stable.
And there's no go-to.
Oh dear.
Okay. Now let's do simple demos. Unfortunately, I don't have I don't have the little thing so I can put this on a projector, but I've got stuff I can show on here. Okay.
Is that a mini PV adapter?
No, this is a MacBook which has its own little
right,
connector in it.
Right.
If it was mini DVI, the problem would be easy because many other people.
What's their mini?
Right. I'm a poor programmer. Okay. So if I just okay, to achieve life example, to put the data into it, in the original graph, in the original slides, it said it was basically a log n performance, which means it could take several minutes to put in that much data. But in this case, I'll just put it up to the query. Okay, insert into the graph. Org ID, des ID, select from the tree of life, the parent ID, and the ID. Okay, so that there will just insert one edge, and then you basically do the same thing again, but reverse these two around to, or can just, but you reverse the parent ID and the ID to get the other. Oh, keep pressing the wrong key. I'll delete. And that will insert the other side of the edge. And like I said, that only takes, it takes less than a second now on the current code which exists on Launchpad. And so now you have a graph of, do select, count, star. Oh dear, I didn't optimize the count. Yeah. Okay, don't do select count. That doesn't like it. In this case, I didn't optimize some stuff in it. Okay, good to know. Okay. So anyways, graph traversal. In this case, this is a more complex join, so I can put in the name of where I want to start and the name of species I want to finish. And that traverses the graph, in that case, in 0.03 of a second. And that, most of that time is actually in the protocol overhead. So on the tree of life, that's only, like I said, 170 odd thousand edges. You can typically do 100,000 traversals a second.
That's pretty good.
Well, like I said, the code is all open source, so have fun. There's actually a good place to look at. There's a forum which Arian set up for people to discuss their experiences with the graph engine. So openquery.com forum OQGraph, and there's a basic forum where people can upload, post messages about their experiences of the engine. Okay.
Great. Thank you.
Yeah.